Hey folks, let's dive into some problems. I have two problems here, one having to do with rolling motion and then one having to do with escape velocity. So this energy problem here for rolling motion probably goes a little bit beyond what you would do on a typical problem, although it might not anymore. I mostly just want to show you the thinking behind all of this. So we're going to make a little picture here, because I forgot, of a sphere that's rolling down a ramp. The only purpose for drawing this picture is to show you that there's a height to the ramp, and that height is important. So the sphere starts at the top of the ramp and rolls all the way at the bottom. When that sphere gets to the bottom, its center of mass has a certain speed, v. And so we are going to derive an equation for the height that results in that equation, that speed v. The most popular way that this situation gets into an AP problem is to have you think about the sphere or disc or hoop or whatever it is rolling down the hill, and then comparing that to like a block of ice or just a block that's not experiencing friction. So we will analyze this for energy. At the top, the sphere has not started to move yet, and so there is only gravitational potential energy. By the time the sphere gets to the bottom of the ramp, it has lost all of that height, which means the gravitational potential energy has been all used up, and there's only kinetic energy left. Okay, I'm having some technical difficulties here, so I'm trying to splice together a couple of videos, and I ran out of paper, so I'm going to try and recap what I did. So, when the sphere moves from the top to the bottom, it has, rather at the top, it has a gravitational potential energy of m times g times h. For kinetic energy, there are two things that have happened. The sphere has translated from the top of the ramp to the bottom, which means it has gained translational kinetic energy. And also, the sphere was not rotating when it was at the top of the ramp, but it has gained rotational speed as it has rolled, and so it also has rotational kinetic energy equals to 1/2 omega squared. This is the moment where we're going to apply our rolling motion, because we are here to solve for h, and in terms of the masses and the linear velocity. And so I have that angular velocity, and the linear velocity is related. So the linear velocity of the wheel itself is equal to the tangential velocity of a point on the surface of the sphere. And I have an equation for that. The velocity of the center of mass of the wheel, which is just v, is equal to the radius of the wheel times its angular velocity. So I can make a substitution and say that the angular velocity is equal to the linear velocity divided by r. So I'm going to make a couple substitutions here, and then we're going to reorganize this equation. So mg times h equals 1/2 mv squared. That doesn't change. In the rotational kinetic energy, however, I am going to substitute two things. The rotational inertia was 2/3 mr squared. And so I'm going to get rid of iota and put in that expression. And the angular velocity is omega squared. Well, that's going to be equal to v squared over r squared. So I have a pretty complex looking third term in that equation, but there's a couple things I can do to make this look simpler. If I look, there's 3 terms, and every term has the same mass in it. So I'm going to cancel m from each term. This third term has a 2 and a 2, numerator and denominator, so I'll cancel those. And even better, r squared and r squared, so 1 in the numerator and 1 in the denominator. So things get a lot simpler right now. I'm left with g times h equals 1/2 v squared plus, and then what's left here is 1/3 v squared. And so that's dealing with adding fractions, so we'll do adding fractions for a moment. 1/2 and 1/3, the common denominator is 6, so that's 3/6 and 2/6. That's 5/6 v squared. If I solve this for h, I get h equals 5v squared over 6g. Once you've done one derivation like this, you've done them all. If you get another question about the sphere rolling down the hill and then it changes the shape, the only thing that will change is this fraction, the 5 over 6. It depends on what the expression is for rotational inertia of that object. Okay, and we're going to look at another problem now. This one's about escape velocity, and again, I had written on this already, and then I lost the video, so I'm going to cover up what I've done since I'm out of paper, and then we'll solve it together. A rocket has an escape velocity, VE, based on the masses of the rocket, the Earth, and then the Earth's radius. In terms of VE, what's that same rocket's escape velocity on Mars? And it gives the percentage of Earth's mass and radius that Mars has. So I'm just going to assume that you have the equation for escape velocity memorized. You can just like rattle it off. VE equals the square root of 2gm over r, and that you can just deal with that right away. If you don't, you have to derive it. So maybe this is a problem where you derive it first and then use it. Now I have to compare this velocity to the new one. And so Vm is going to have the same equation, but it's going to change the value of mass and radius. And so I chose percentages because it's been a while since I've had a problem with them. So 2g doesn't change, but the mass is 53% of Earth's. Well, 53% is 0.53, so it's going to be 0.53 m. And then same thing with the radius, 11%, that's 0.11 r. Okay, so I have to figure out what Vm is in terms of Ve, and so I'm going to separate out what's in the radical into two radicals. The first radical is just going to be 0.53 over 0.11. Now, it's really important that you understand why the 2 didn't come along with it. I've answered this question a lot all throughout the year. It's a really common question in this course. The 2 doesn't come along here because the 2 is a part of the equation. The 2 is not something that tells us anything about Earth or Mars. It only tells us about what the definition of escape velocity is and how you would calculate it in general. So that's not going to tell us the relationship. The numbers I put in, 0.53 and 0.11, they are important. And so everything that's no longer important is going to go in this second radical, and the coincidence, which is not a coincidence, is that I have 2gm over r, which is the exact same thing as the equation for escape velocity. So what I mean is I'm going to calculate this first radical. The square root of 0.53 over 0.11 is 0.46. And the square root of 2gm over r is Ve. It is the escape velocity on Earth. So this escape velocity on Mars is a little less than half the escape velocity on Earth. And that is how you would deal with percents and escape velocity.